also the
Hello.
CE Distinguished Speaker Symposium. And this event is sponsored by the Center for Efficient, Scalable, and Reliable Computing, called CESAR. And it's my pleasure to welcome you and to welcome our speaker, Professor Josep Torrellas. Josep and I were in graduate school together at Stanford a long time ago, and he has, so he's had this is his first visit here, but he has ties to other faculty in the department as well. He's Ph.D. advisor to a couple of our faculty. So Josep is a professor of computer science and, by courtesy, electrical and computer engineering at University of Illinois at Urbana-Champaign. He's a fellow of the IEEE, and he's a fellow of the ACM. And he's director of the Center for Programmable Extreme-Scale Computing, which is a DARPA-funded center of DOE and NSF. Focuses on architecture for extreme energy and power efficiency. And he also directs the Intel-Illinois Parallelism Center, a center created by Intel to advance parallel computing in clients. And he's made lots of contributions to computer architecture and shared memory multiprocessors, cache hierarchies, coherence protocols, thread level speculation, all sorts of things. So it's our pleasure to welcome Professor Torrellas to today's talk. So he's asked that you can ask questions during the talk if you like. So.
Yes. Yeah, so thank you, Greg. Thank you, students and faculty, for attending this colloquium. So as Greg said, this is my first time at NC State, and so I'm very happy to be here. In this colloquium, I'm going to try to give you an overview of some of the work I've been doing with my students in the last 3 to 4 years on variation-tolerant computer architectures. Okay? And as Greg said, please stop me and ask me questions during the talk. Okay? So what's the big deal about variation-tolerant? What is it first, and what's the big deal? So the motivation for this is that Moore's law is alive and well. So every generation, we're getting more and more transistors on a chip. However, these transistors are becoming lower quality transistors. And the reason for this is that they're becoming harder to manage, and they're becoming kind of less reliable. Okay? And in particular, a problem that is worrying many people in industry is what's called process variation. Okay? For those of you who have not heard this term, process variation, what this means is that if you look at the parameters of a device or a transistor in particular, they're not the same when you build it as the nominal specifications. Okay? Instead, they vary. Okay? They deviate from the nominal specifications. So for example, some transistors become slower than they should be, others become faster, others consume more power, others less power. Okay? So that's process variation, and it becomes the impact of process variation on many cores is very worrisome, is that they have spatial and temporal variation. In spatial variation, it turns out that different cores in a given many core will have different frequencies. So if you look at what is the max frequency that a core can support, some corners of the chip will be faster than some other corners. Okay? And also, some will consume more power than others. Okay? And this is becoming a big problem now already because there's big differences, and looking forward in the next few generations, it's going to become even more. Okay? There's also temporal variation, which is the fact that as processes are being used, they become slower. Okay? So it turns out that they wear out or they age as they execute. So we're going to be worrying about these things and see how we can handle them. The key question, of course, is how to handle variation in the most cost-effective manner. And that's, many people are working on this area. And it turns out that most likely, the best way to handle process variation will be with a combination of circuits techniques, design techniques, architecture techniques, or even software approaches. Okay? Maybe the runtime system can isolate you from these variations. In this talk, I will explore some of the architectural solutions that we've been looking at the University of Illinois. Okay? I'm going to try to give you a slow startup, an overview of the problem. If you feel lost or you have questions, please stop me. Okay? So the way I'm going to organize this is, first, I'm going to try to understand how to model process variation, okay? So that we get a handle on the actual, how it manifests. Then once we understand this, we're going to be looking at how to mitigate process variation, both temporal and spatial variation. Sometimes we cannot mitigate it and we'll have to just live with it. And so how do we leverage or exploit process variation as it is? Okay, that will be the third part of my talk. And then towards the end, I'll reconsider this in the context of more aggressive technologies, like technology called near-threshold computing, which is an environment where I reduce the voltage quite a bit, and then process variation becomes much more of a problem. So depending on timing, I may spend more or less time in the last topic. Okay? So the first thing is, how do we go about modeling temporal and spatial process variation? Okay? So in the last few years, we have been developing models of these effects. So we have a model called Various and Various NTC, near-threshold computing. These are models that model process variation, spatial process variation from a microarchitect's point of view. Okay? And we have Facelift, which models temporal variation. Okay? I would encourage you to download if you're interested, okay, and play with them. Let me give you an overview of how it works, how we go from device-level models up to microarchitecture model. Okay? So it turns out that process variation is divided into die-to-die and within-die process variation. This is a wafer, and a wafer has different chips, and there is a die-to-die variation. But we're going to focus on within-die process variation. You give me a chip, a die, and then we're looking at what is the variation inside. Okay? And we're looking at a few key parameters. For example, the threshold voltage of the transistors in the chip, okay? Or the effective length, the gate length of the different transistors on a chip. How do they vary? Typically, people who deal with this, device physicists and so on, they divide variation into a systematic source, systematic effects, source of systematic effects, and then random effects. Okay? Systematic effects are due oftentimes to imperfections in the tools or the lens that people use to fabricate these chips. And so they have spatial correlation, which means that the properties of a transistor at this point are very related to the properties of nearby transistors. Okay? So there is some spatial correlation in these properties. On top of that, there is a random component of process variation that comes from more random effects. In particular, the dopant densities, the dopant atoms, as they fall into the semiconductor, they have a random effect. Okay? So we're going to have to model both effects, and the combination is process variation. So with Various, we're looking at within-die process variation of both the threshold voltage and gate length. Okay? So how do we model systematic variation? So here, we logically divide the chip into a grid, and then we consider a value of within-die process variation and channel length for each of the grid points on chip. Okay? And we use a normal distribution for each point. So for a given point in the grid, we need to assign the value of the threshold voltage and the L effective, and we use a normal distribution with a certain sigma and standard deviation, mu and sigma, mean and standard deviation. And we get these parameters from the international roadmap for semiconductors or from talking with industry. Okay? So you get this, and also there is a correlation between the different points. So not only you have to worry about a normal distribution of the values you assign to a given point, but also the points that are around that, which also distribute normally, have a certain correlation. Okay? So you have a multivariate normal distribution. And the correlation that we use, talking with industry and looking at some of the papers, is a spatial correlation, which means that two transistors that are nearby have a correlation of 1, meaning that they have the same systematic component of their variation values. And as you move away from that transistor, the correlation becomes lower, following this curve, and then at a certain distance phi, which may be a small fraction of a millimeter, then becomes 0. So the two transistors are not correlated at all. So that's for the systematic, and then we have the random component. This is modeled analytically because random can take any value. Again, it's a distribution that is a normal distribution with a certain sigma and a certain mu, but it's random. Okay? So two different transistors are not correlated. And then you assume that the two components are totally independent, so that you add the variance, the systematic and the random, and you get the final sigma. Okay? So you have a mean and a sigma of the resulting system. So with this very simplistic model, we come up with a distribution of the threshold voltage and the channel length across the whole chip. Okay? And you take another chip, and then you get a different distribution, and you get another chip and a different distribution. Okay? Now, the interesting thing is move upstream. So how do we use this thing? The first thing is take a pipeline stage. A pipeline stage is composed of a set of logic paths. Okay? And we want to figure out what is the distribution of the latency or the delay of a logic path in a pipeline stage. Okay? Let's start with logic stages. With logic stages, we have a bunch of gates, right? You can compute that. You can look at the design of a pipeline. And then here, you take a certain fraction of the time is due to wiring. And let's assume that wiring doesn't vary, doesn't have process variation. And then we have a certain fraction that is due to gates. Okay? Now, there are formulas that give you the gate delay. Okay? The delay in which a gate switches as a function of some of the transistor parameters within that gate. So you'll notice here that we have the threshold voltage of the transistor that was in this gate, and we have the L effective of the transistors here. Knowing the process variation of these parameters, we can actually have a distribution of the gate delay, the switching gate delay. Okay? So different gates, depending on where they are placed on chip, will have different speeds. If we put all the gates together here, then we need to add the systematic components, okay, which typically will be the same because they are nearby. And we need to add the random components. The random components will tend to average out. Okay? So what do we get from here? Let's take a pipeline stage. Let's take the distribution of the path delays of a pipeline stage. This is the solid line here, no, the dashed line. So this was the distribution before process variation. Okay, so this is a density function. So if we move this way, we have longer latencies of the paths in this pipeline stage. So as you know, this is the period of the pipeline. So all the paths have to take less than the period, and there's a certain distribution. If I add this model of process variation, I will find that some paths become faster, some paths become slower, right? So I'll have a curve that becomes basically flatter, like this. Okay? Some paths become faster, and some paths become slower, which means that the process, this pipeline stage, will need a longer period to be able to cycle without errors, right? So basically, we have a TVAR. TVAR is the new period, the safe period. Okay? So with this model, we can figure out, knowing the sigmas and the mu's and the phi's, we can figure out what is the safe period at which I can cycle this pipeline stage, depending on where on the chip the pipeline is laid out. Moreover, if I insist at cycling that pipeline stage at a period t that is less than the safe period, okay, then I can figure out what is the probability of a timing error by looking at the area under the curve. Okay? So in here, obviously I have no errors, but if I move this way, I increase the probability, and if I get to the point where, for example, here, that was the safe or the no variation period, then I have many more errors, higher probability of errors. So with this model, then it can give you not only the safe period, but also it can give you what is the probability of finding a timing error for a certain pipeline period. We do the same thing for memory. So some of the pipeline stages, actually, you access the cache. Okay? So then we need to figure out, based on the transistor parameters of, say, this is an SRAM cell, 6-transistor SRAM cell, I can figure out what is the variation in threshold voltage and L effective of these transistors, and I can figure out what is the latency and what is the variation. Okay? And I can do the same thing here for memory accesses. And then at the end, I have this processor that has a bunch of stages, right? And without variation, the pipeline stage delay was distributed like this. So a lot of the pipeline stages had similar delays. Because of process variation, some pipeline stages become faster, others become slower, right? And so what happens at the end is that because a processor the frequency of a processor is determined by this lower pipeline stage, the bottom line is that process variation ends up slowing down the processor frequencies. Okay? So you give me the processor without process variation, it can cycle at a certain frequency. With process variation, it will cycle at slower frequency because it's determined by the slowest path, right? So even though we will have a variation in the frequencies across the whole chip, most likely all the cores will be slower than they would be otherwise without process variation. Okay? And I can do a similar thing with static power. This model also handles static power. And what's clear is that even though some transistors become less leaky and some become more leaky, okay, they consume more leakage power, it turns out that those that save leakage, okay, save less leakage than those that consume more leakage end up consuming. And so the bottom line is that overall, processes consume more leakage power. Okay? So this is the effect of process variation. Cores become slower, they vary their frequency, and cores consume more leakage power, okay, more static power.
So how much slower are we talking about?
Well,
just sort of range.
it depends on what is the technology and how many cores do you have, right? So the variation that people observe now for 32 nanometers say, okay, all the models seem to say maybe 15%, 20% frequency variation, okay? Power, static power is much larger, maybe 50%, double, right? If you listen to Shaker Borker, they show humongous variation in leakage, okay? As we look forward to smaller feature sizes, all these things get augmented. So 11 nanometers, you may get maybe 3 times the leakage power. As far as frequency, maybe double the frequency. Any other questions so far?
Here you're saying that without process variation, you have cut off on the delay of the state.
Yes, yes.
But when you apply, so first of all, how is that? Like, how can that be? It would be a normal distribution too, or you are saying that the upper limit of the delay that transistor will have?
So when you go at, you look at the design of a processor, right? There's a bunch of paths, right? And then you time all those, and you get a certain distribution. So you get this
Across many
many paths. Yes, yes. So this is all the set of dynamic paths in a pipeline stage. That's the whole distribution, right? Right? You get this from the tools. You go to a company and they give you, well, no, they don't give you, but if you work there, you see this distribution, right? Yeah.
How is the capturing of this distribution different from what we do using different library sets like worst case library conditions? Using such as a worst case library condition that determine the frequency of the cycle.
Okay, so probably this library that you use, they don't consider process variation, perhaps, okay? So what they do is they look at the worst possible combination of inputs that will make how long it will take the longest critical path for the worst possible input, right? On top of that, you have to augment this model with process variation, right? Knowing that in the worst case, right, some of the gates that are in the critical path will end up being slower. Right? So there are tools now that try to put some of these models into CAD tools. Eric, you had a question?
So the SRAM cell?
Yes.
Is it that things would slow down or go faster? I would think that variation there is more of a stability issue. Things would fail or work.
Well,
The way that's
somebody take the phones. so it turns out that there are many problems, right? There are many problems. So there is read timing, right? There is write timing. There is write stability, meaning if you have the signal may lose with time. You may lose the signal, right? So you have to take into account 6 different types of errors, okay? Especially as you go to low voltages, then we use 80 cells because this thing becomes just unreliable at low voltage. Okay, so we model all 6 types of errors.
For any, you say we have parameters like sigma and this thing for different technologies. The values that you observe, is it taken from the specific manufacturing process, or how is it exactly valued?
So typically companies keep these numbers secret, right? So you get it from the ITRS, which is a public document. These are estimates from the semiconductor. It's probably off oftentimes. Then speaking with some of the people in industry who are more willing to give you hints, right, that's where you get it from.
So this is going to vary across different technologies or different manufacturing?
Yes, certainly, certainly.
It may happen that it gets worse or it may get better.
Correct, yeah. So this is as far as spatial. Another interesting thing is temporal variation. It turns out that the transistor delay gradually increases with time under normal use. Okay, so what does this mean? That these critical paths become longer as processors execute. Okay, so initially, I'm going to plot here the critical path delay versus time in years. So first year, second, say until 5 years, which is service life of a processor. Okay, so initially, the critical path took T0 nanoseconds, if you want, right? And then as processors execute, the critical path increases with time. Okay, and that's why we have a guard band. Okay, that's one of the reasons for the guard band. So when manufacturers sell a processor, they don't say cycle it at this frequency, at the inverse of this, okay? Even though it could cycle at the beginning of the service life, it could cycle at this, they tell you cycle it at the inverse of this, right? They give you the frequency that the processor will be able to support at the end of its service life, okay? Which means that you're wasting some of the time, right, at the beginning of the service life. Make sense? Now, this, again, is kind of a secret thing. What is the guard band? In fact, there are multiple reasons to why you put the guard band. But maybe for aging, you get 5% plus, 10% maybe. There are multiple mechanisms that affect how fast the processor age. Okay? One of them, so there are a couple of them that seem to, the people who understand this topic seem to point out as dominant. One is bias temperature instability. Okay? Another one is hot carrier injection. The key point in these things, in these techniques, is in these effects, is that they follow a power law with an exponent less than 1, which means that they seem to age quickly at the beginning and then they saturate. Okay? So they follow this type of curve. It turns out that BTI also has some recovery, okay? Depending on the polarity of the transistor, what logic value you put in the gate of the transistor, it goes into some recovery mode as opposed to stress mode. Okay? But that depends on the actual logic values. But overall, it follows this. It doesn't recover completely. It follows this curve. Okay? So fast at the beginning, then desaturate. Okay? The important thing to note here is what affects the aging rate. Okay? What affects the aging rate is two main parameters: the supply voltage, or actually supply voltage minus threshold, and the temperature. Both are key parameters. Okay? They affect exponentially the VTI, and the HCI is affected exponentially by the voltage and linearly by the temperature. So what does this mean? It means that if you have a processor and you put high voltage, it ages faster. Okay? Put a lot of stress. Same thing, if you use high temperatures, it ages much faster, okay? Exponentially. So if you want to keep the processor young, right, you want to keep it in a cool place, and you want to keep it with low voltage. Okay? It makes sense, right? So if you had routers and other systems in high temperature, they fail soon. Okay? So we're going to keep this in mind whenever we try to muck around with these parameters. Okay, so now we understand the basics of both spatial and temporal variation, and then we're going to try to find out how to modify, how to mitigate them. Okay? So there are many techniques that we've looked at, and they come, across the whole system stack. I'm going to focus on one that is at the low level and one that is at the high level. Okay? So at the low level, there's something called body biasing. Okay? And the idea here is it's a well-known technique that allows you to control the threshold voltage of the transistors. Okay? So physically, it's done by applying a voltage between the source or the drain and the substrate of a transistor. And the effect of this is that you change the threshold voltage. Okay? So if you apply forward body biasing, if you apply a certain polarity of the voltage, then the threshold voltage decreases for that region of the transistors in that region, which increases the frequency of the processor, but also increases its leakage. So that's a way of making that part of the chip that was slow, making it faster at the cost of leaking more. Okay? You can apply reverse body biasing, where you effectively increase the threshold voltage of that region, which reduces the frequency of the transistors or the processors and decreases the leakage. Okay? So that's, if you think about it, it's a key knob that allows you to change the speed and leakage power. Okay? We know about another knob that is very useful, which is DBFS. With DBFS, we change the frequency and dynamic power, correct? So we speed up the processors, but we consume much more dynamic power, right, by increasing the voltage and frequency. But we can save dynamic power by decreasing the voltage and frequency. Now, this is another knob that allows you to change frequency for leakage power. Okay? So basically, that was popular a while back. Nowadays, it doesn't seem to be very useful because of some of the material issues. But in the future, it may be useful again, is to apply body biasing. So if I have this chip here, and I have this part here that is particularly slow, and this part is fast, then what I would do is divide the chip into body biasing cells, right? And slow cells receive forward body biasing so that they can speed up, and the leaky cells receive reverse body biasing so that you save leakage. Okay? So in this case, what used to be yellow or white here and then dark here, I've been able to compensate. So the result is reduced within die process variation, both in delay and in power. Okay? And we can even think about changing the body bias voltages dynamically based on the workload. If one part of the chip is being used by a high power consuming thread, you can change the body biasing. And of course, that has implications on circuits because we need to have ways of measuring how close we are to the cycle time. Okay? So if there is a lot of slack, then I can increase the speed. Okay? But if there's not a whole lot of slack, then I have to go back. Some of you may know about the Power 7 processor. IBM Power 7 has ways of measuring what is the slack in the cycle time and dynamically change the frequency to get closer, or reduce the voltage to save power until it gets very close to the cycle time. Okay, so these are currently used techniques. So this is a technique done at the circuit level. We can do it at the upper end of the stack here. We can have the runtime or operating system know about the profile of process variation within a chip, right? Maybe even the virtual machine monitor knows about this thing, right? And so we can schedule the jobs according to what is the distribution of speeds and power. For example, if our goal is to reduce power consumption, then we might want to map those applications that consume a lot of dynamic power, those that do a lot of computation, for example, in processes that leak the least. Okay? That will kind of balance the power. Or if our goal is to improve the throughput, we may want to map those applications that would benefit from fast processors, okay? Those that do a lot of computation as opposed to waiting for memory, map them in cores that can cycle at high frequencies, say the red ones here. Okay? So that's something that it potentially has a big impact, because with the process variation you get frequencies that are significantly different. Okay? So that's another example. What about temporal variation? Now this is a very interesting problem here. So if we think about this, I said before that we get a initial change that is very fast, and then towards the end I'm going to saturate my aging. And we know that voltage is a big effect on aging, right? If I reduce the voltage, what happens if I reduce the voltage applied to this processor? Okay, so I have a processor and I reduce the voltage without changing the frequency. What happens if I reduce the voltage? It slows down the aging rate, as I said before, because the aging rate is exponential on the voltage. So the slope at which I'm going to be aging is decreased. But at the same time, if I decrease the voltage, the gates become slower, right? So remember the formula I showed a while back in this corner here. It had the switching speed of a gate was proportional to the voltage, right? I reduce the voltage, it increases the delay of the logic paths, but it slows down the aging. So I'm going to start, this was the critical path. Okay, the critical path started here. This was at the beginning. I'm going to start with slower critical paths, but they're going to age at a slower speed. If instead I increase the voltage, what happens if I increase the voltage, okay, without changing the frequency? First, okay, not going to give it up yet. So first, it reduces the delay of the logic paths. So I'm going to start down here faster, but I'm going to have a much higher slope like this. Okay, any questions on this? I'm trying to see how we can actually affect the aging. Okay? So if I increase the voltage, it's going to age faster, but the circuits will be faster at the same time. If I decrease the voltage, the circuits will become slower, but the aging rate is also slower. Okay? So I can modify this quite a bit now. When do I apply these techniques? So the aging rate is higher at the beginning and lower at the end. So I want to apply low voltage at the beginning of the service life of the processor. So in the first year of the processor, I can apply low voltage. What happens? That's the point where I can affect the slope the most. Okay? That's when it's most sensitive to the voltage. So if I do that, then I'm going to slow down the aging the most. And because I have the whole guard band for me at the beginning, I can afford to slow down and start. I have a lot of room. I can start much at higher latency. Towards the end of the service life, the last 4 years, or the last 2 years, say, or 3 years, I can then start cranking up the voltage. Why? First, because I cannot affect the aging rate much more because it's already saturated. And second, at that point, I have consumed most of the guard band. So I need to make sure that I speed up the circuits. Okay? Remember that when I put high voltage, then the circuits become faster. So I get something like this. Okay, questions here. Does this make sense? Yeah.
So you're applying this VDD scaling to impact aging based on elapsed time, essentially, age.
Yes.
However, that might not actually correspond to the real wear out of the circuit. So it would be perhaps better if you had the way to measure the aging in real time.
Oh, you got to do that.
Some kind of odometer for the circuit. I know there's some research in that area as well.
We have to do that. We have to measure how close you are to how much have you aged so far, right? And it's not just research, it's actually in a product. This IBM Power 7 has these odometers. So they have in the critical paths inserted these things so that at any time you know how far you are to the end, right? And yeah, there's a lot of research as well on how to make this very efficient and distribute it so that you don't want to make a mistake, of course, right? So that got us thinking about what can we do with this. Yes?
So, if I'm not wrong, you would hit the guard band eventually, is that correct? You would hit the guard band no matter how you change the voltage, is that correct? Even if you start at lower voltage.
No, maybe not, maybe not, maybe not. So I'm going to try to argue that you don't, if you are careful. So, any other questions? Yeah.
These curves that you have, this is all based on measurements in Power 7?
No, not measurements. This measurements using a model.
Model.
Yeah.
I guess I'm just surprised that you get this result. It's sort of like implying that if you, let's say you ran a circuit at, I pick a voltage, so let's say 1 volt, and you ran it for 10 years, you're going to have like that upper curve. But then if you did nothing with the circuit, same chip as instead of running it for 10 years, you just started doing nothing for a year, then you turned it on and ran it for 10 years, that you're going to be at a lower point at the end of 11 years in that second case compared to the first one.
So, sorry, I don't know what you mean by this. So in both cases, you are aging for 10 years, right?
Yes.
So it should be the same slowdown, no? If the first year you keep the machine off,
Yes.
why would it age?
Well, or kept it at 0 or very, very, very low voltage or...
Well, so
So then what I would expect then with your curves is that you'd see that bottom one approach.
this one?
See it approach the upper one.
Not necessarily, because
Voltage was the same towards the end.
no. So I'll give you more insight in a second, right? But it matters how you exercise the processor. Okay, so let me continue and then maybe you can ask me a bit later. Any other questions? So this got us thinking about the following. Okay, I'm going to leverage this thing. Current processors are sold at a certain frequency. Okay, so this is the period, right? So at the beginning, when they are sold, they could cycle at a higher frequency. This is the inverse. This is the period, right? The critical path delay. And then as they execute, they become slower, and they reach this saturating period, right? After, say, 5 years when you throw them away. Manufacturers will tell you that the processor can only cycle at this frequency, right? The inverse of this, right? Even though at the beginning it could cycle faster, okay? That's because we have a certain voltage that we keep constant from the beginning of the service life. There is a waste here. There is a wasted opportunity, right, of this extra guard band that is there. Okay? At the beginning, when you run the processor, the first year, the processor could run faster, but you don't run it because there's this guard band, right? With time, it will age and it will reach this thing. Can we do something here? People who overclock processors have already figured out some ways of playing with this, okay? But this is a missed opportunity. And what we want to do is we came up, well, so if you think about it, you can do age management. Okay? We could manage the age and either save power or improve the performance. Okay? Let's see how this works. So this wasted opportunity, if we are willing to continuously change the voltage as the processor is being used, okay, with time, okay, and that will require that we have monitors that monitor things so that we don't make a mistake, right? But if we are willing to play with the voltage without changing the frequency, we can translate this into power savings, what we call DVS, dynamic voltage scaling for age management for power reasons, or we can translate this into higher frequency. So the same processor, if we're willing to play with the voltage, we can run it at the frequency that Intel sold it to us, but save power, or we can cycle it throughout the whole life at a frequency that is, say, 15% higher than what Intel sold it to us, and still run it safely. Okay, so let's see how this works. Okay, then you tell me if it makes sense or not. Okay, so let's start with DVS-AM power. Okay, here. So here my goal is to take the processor and cycle it at the frequency that Intel tells me, but I'm going to be changing the voltage and save power overall. How do I do this? So before I kept the voltage constant. Why don't I, when I start using the processor, start with very low voltage, okay, not very low, but so lower voltage, right? And then with time, increase the voltage. Okay, so every month or every 3 months, keep increasing the voltage. Okay? So what happens here? So this is the new voltage, right? Now what happens here? At the beginning, so this is the best that I can do, okay? This is the best I could do. So I'm going to be reducing the voltage as low as I can so that at time 0, I already consumed the whole guard band. Okay? So rather than my critical path slowly going this way, I'm going to just, by reducing the voltage, I make the circuit slower, but I'm going to consume all the guard band. Okay? For this frequency in which I'm running, I'm going to hit the max delay. Make sense? The aging, yes?
Do you have an underlying model of how the y-axis may behave with respect to the voltage, or are you just doing it arbitrarily to see the steepness?
Okay, so we have models for that, but at the end of the day, you'll have to have monitors in the pipeline that monitor this thing, right? And so this, obviously, is the best case. You hit the whole period, right? So you slow down, you reduce the voltage so that you slow down the circuits to consume all the guard band. And then, because I'm at such a low voltage, the circuits age slower. And therefore, I can keep slowly increasing the voltage, and I can keep at this point. Okay? So this is the best, the ideal case, right, where I will be able to keep the critical path delay to be equal to the max period. Okay? Such that towards the end, basically, I have all the time. So the trick here is to have, at every single point in time, consume all the guard band. Okay? You can see here that rather than cycling at or applying this voltage, I have had this voltage across the lifetime. That means humongous savings in power, okay? Because the power is, depends on quadratically on the voltage. Okay, so I've been able to save a lot of power for this. Okay, so critical path delays are kept at this until the end, and you save a lot of power. Now, what if I want performance? So what do I do? Now here I want Intel sells the processor at 1 gigahertz or 3 gigahertz, and I want to cycle it at 3.5 gigahertz throughout the whole life at the power cost. Okay, what do? I will start with slightly low voltage and then quickly increase the voltage. Okay, so that, remember that this was the critical path delay, and this is the period of the processor. Now I'm going to say I'm going to reduce the period throughout the service life. I'm going to increase the frequency and so decrease the period across the whole service life, not just at the beginning, but throughout the life. Okay, which means that first I'm going to reduce the voltage, right, here, and so the circuit will become slower. I will hit this point, but then very soon I'm going to have to increase the voltage and make it so that I can make it faster. So it never goes above this period. But because at the beginning I had a lower voltage, I reduced the aging rate. And because of that, I can afford not to go past this value. Does it make sense? Because I was able to affect the aging rate at the beginning significantly, I'm now able to increase the voltage and not go past this new smaller guard band.
I'm not a computer engineer, so my question may be a little off track. So what I was trying to ask is that the design of this manipulable input that you're doing, like because the voltage, I guess.
Voltage, yeah.
So is that done as a planning problem, or is this online? Like as the tau is varying, you change your V accordingly.
Yes, right. So you would do it on the fly. Yes, on the fly in real time. So you would do it every 3 months or so, right? You would model, well, you would measure how close you are, and you would say, now I have been running a lot of work, and it's this close now, so I'm going to increase the voltage this much. Yes?
Here from the graph we can see that the critical path delay at some point of time will be equal to tau d, right? That is the maximum limit of.
You will never get to this point anymore.
So is that more like a tangent to that critical path curve, or?
You're asking in general? How? So, yeah, I mean, the important thing is that it's fast at the beginning and then it saturates towards the end. Okay, so where the tangent is, I don't know, it may be 7 years or whatever, or more.
So from a manufacturing point of view, your machine will always keep on running.
Yes, yes, of course. Yes. Okay, so what we've done here is, at the cost of a significant more power, right? Because now I have higher voltages for much of the service life, okay? But I can do better. So this is a shorter critical path delay until the end, so it runs at a higher frequency at an increased power, okay? But I can do better than this. What if I'm willing to throw away the processor after 2 years, okay? Rather than keeping it for the 5 years, okay? In that case, I can actually increase the performance much more, okay, at the cost of more power, okay? So here is the idea. Suppose I want to just throw the processor away after S short, okay? I have here the original curve and the curve with the previous slide, okay? DVS AM perf. Now what I'm going to do is I'm going to decrease even more the period of the processor, okay? I'm going to decrease it more. And so I'm going to have to start first at lower voltage, but increase the voltage right away, okay? And as I increase the voltage, then of course I'm able to keep the critical path below this new time. But because it's aging very fast, then there's a point where I cannot support this anymore, okay? And I have to throw it away. So only up until a certain duration, maybe the first year or 2 years, 1 year, I've been able to crank up the voltage, consume a lot of power, but cycle it at high frequency, okay? Again, those who do processor overclocking already do this, right? So what do? They crank up the frequency and the processor, right? And then after a year, they have to throw it away because it doesn't work. That's what happens here, okay? So they have aged the processor. So even higher frequency for a short service life. Okay, questions?
Just a comment. I think it's a little bit dangerous. The insights are a little bit dangerous. Like the manufacturers will know, like, you want to buy extended warranty 3 years or just 1 year. This 1 year is, pretty much crank up the voltage so that it dies after 1 year.
That's fantastic and perfect whenever you have many cores. So what happens nowadays? Nowadays we have chips that will have 64 cores. Many times you're not going to be able to use. In fact, you won't be able to power all the 64 cores at the same time, right? So here's a way to use the 64 cores of a machine. First, so we're going to try to use, the power aspect of this technique to increase the throughput during the parallel sections. And we're going to try to use this throwing away of cores at high voltage to speed up serial sections of programs. Okay, so I have this chip here that has, say, 64. I don't know how many it has here, cores. And I just cannot power them all at the same time because the power envelope is not enough. Okay, and this happens nowadays and it will happen more in the future. And it's a homogeneous many core. Okay, no need to put accelerators or anything. Just take this. You pick the most power efficient of these 64 cores, let's say 16 of those, the most power efficient, okay? And those, you run the parallel sections on these codes. Okay, those are the ones that reach the power envelope. You cannot power more than 16 cores, say. In fact, if you do this thing, you can power more than 16. Maybe you can power 20. Why? Because we're going to change the voltage and we're going to save power, right? DVS AM power. And by this power that we save, we can increase to 20 cores. Okay, so the parallel sections will run with 20 cores as opposed to 16. Okay? Make sense so far? And then, once we run sequential codes, okay, codes that don't need parallelism, then we're going to shut off the other ones. This we call expendable cores, and you just run the sequential sections here. You crank up the voltage and frequency for those, and then you burn them, say, after 1 month. Okay, so since you have 30 cores that are expendable that you don't know what to do with, right? So you run them at high frequency and voltage, and you throw them away after a month. And if you have 30 of these cores, you have 30 months, you know, nearly 3 years worth of processing. Okay, so that's the high-level idea. You pop them like a bubble wrap, basically, and you discard them due to aging. Okay, this is not that hard to build. You just need 2 rails of power. You need the main power and then a high voltage. High voltage. And then you just connect the core to this high voltage, you use it, and then you throw it away. Okay, you don't need to know at fabrication time which cores will be connected to which. You just connect all of them, and then you pick the ones that you do. Yes, Eric?
Especially in the parallel context, you don't have to throw them away. You run them at a lower frequency. Unless they die, unless hard faults.
Yes, yes. So.
You recycle them towards parallel portion.
Right, but the question is, you already have 20 cores that can run the parallel section, and that's already the limit, right? That's the max power envelope anyway. Okay? So that's the idea of the bubble wrap many core. Okay? Any questions? Yeah.
For this simple cores, because this is a many core chip, right? For the simple cores, is the problem of the variance more significant or less?
So it has to do with what is the technology, but as the feature size decreases, then you have more variation, right? If you're asking me whether simple cores versus
I'm asking if you are given this chip with this kind of variance, you can design like a 4-core, or you can design like a 64 cores. Is more important in a 64 case or less?
Okay, at the higher level, if you have simple cores that are small area, then that thing will contain only one neighborhood. So you're going to have more variation, more faster and slower cores. If you have a big core that uses a lot of area, chances are that it will include slow parts, right? And if it includes slow parts, then it means it has to be cycling at the slower frequency. Make sense? So if you have many simple cores, you're going to have more variation. If you have bigger cores, then they become all slower. Okay? So I want to move quickly in 5 minutes to talk about the next thing here. So because power is so important, right, many people now are looking at reducing the voltage. Voltage has a superlinear effect on both the dynamic and the static power. Okay? And so there is an emphasis on reducing the voltage aggressively to minimize power. This is called near threshold voltage. Okay? So basically, rather than having 1 volt, which is what current processors do, with near threshold voltage, you would put only 5 volts as supply voltage, 0.5 volts. Okay? The potential is that it could save you 10 to 40 times the power. Okay? So the power of a core that uses 1 volt and the power of a core that uses 0.5 volts is from 10 to 40 times less. Which means that you could have 40 times more cores or 10 times more cores in the many core powered at a time. So potentially it's attractive. It has lots of problems, but potentially this is attractive. So if I have here the voltage, okay, this is higher voltage, this is low voltage. So here is the threshold. And so near threshold would be about 0.5 volts. And this would be the conventional processor. Okay. So what happens to this parameter? This is the inverse of the energy. MIPS per watt is the inverse of the energy to do an operation. Okay? So I want to be higher here. That's the total energy that I need to do an operation. Okay? So the efficiency goes down like this. So near threshold voltage versus conventional, you consume 2 to 4 times more energy to do an operation at 1 volt than at 0.5. Okay? 2 to 4 times. But the circuits are about 10 times slower here than here. Okay, so that's one problem. So I consume less energy, but at the same time I become 5 to 10 times slower. And that's the reason why the power is 10 to 40 times slower. Okay, so think about this. I run the same operation. The same operation takes 2 to 4 times less energy, but it takes 5 to 10 times longer, and therefore you consume 10x to 40x less power. So that's near threshold voltage. This clear? So what are the issues? The frequency degradation. So many people don't like this thing. Okay, 5 to 10 times lower frequency. And so that means that you're going to want to use this only for highly parallel applications. Okay, so you have to do parallelism to handle this problem. Another problem is the share of static power increases. Okay, remember that the dynamic power is V square F, right? So if I decrease the voltage, the dynamic power decreases significantly. The static power also decreases, but not as fast, which means that by the time you reach near threshold voltage, the static power, the share is much higher. And so you're going to need to re-architect the memory hierarchy, because that's where the leakage occurs. And you need aggressive power management. So that will be a technique that is very important for the future, to do aggressive leakage power management. Already processors do, but we need 10 times more of that. And then the final problem, and now you'll understand why I'm looking at this, is the sensitivity to parameter variation is much higher. Okay? Some people say 5 times more. Okay? The same variation in threshold voltage, say 5%, 10%, changes much more the frequency and the power. Okay? So give me a chip that has the same process variation values, apply 1 volt or apply 5 volts, I'm going to have much more variation in the case of 5.5 volts. Okay? So that's a problem that suddenly becomes much more important. And there are lots of problems here. It's an open research area. So how do we handle variation in this environment that has high variation, NTV? So first, you can do body biasing, as we said before, but it's not applicable anymore. Okay, it turns out that there are some problem with device architectures that make this more questionable. You can also adapt the voltage and have multiple voltage domains per chip. some of them in the fast areas of the chip have higher voltage, in the slowest areas of the chip have lower voltages. Okay? But there are problems here. First of all, on-chip regulators have a lot of power losses. Okay? So you don't want to waste a lot of power by actually supporting these multiple voltage domains to make the system more power efficient. Also, if I have a voltage domain that includes many processors, at the end, these processors are very different of each other, and then you have to set the parameters for the worst of all the processors in that domain. So the bigger the domains, the less the advantage of having these domains. And then there's the issue of voltage groups. So these guys will have low capacitance, and then as I draw and I shut things off and on, then suddenly there will be big drops in voltage. So that's another big problem. Okay? So we're looking at all these problems in an environment where you have near threshold voltage. So we're looking at different many-core designs. So how would you design a many-core in this environment? Well, you would have, first you would organize it in clusters, okay, to exploit within-die process variation. So clusters would be organized around groups of processors with some cluster memory. Okay, some clusters will be slow, others will be faster because of process variation. So basically, the slowest core, each cluster will be a frequency domain, okay? And the slowest core in this cluster sets the cluster frequency. And then in our design, we're thinking about having the cluster to be the minimal unit of allocation, okay? Then the issue is how many voltage domains you have, perhaps just one voltage domain across the chips to make it simple, and then play with the frequency. So there are multiple possibilities here that we're looking at. And that gives me to the last slide here, which is, or the last couple of slides here, is all these technologies that I just described have an implication on the future architectures, okay, what we're going to see next, okay? And one of the, I think, architectures we're going to see next is what people call extreme-scale computing, okay? What is extreme-scale computing? So an extreme-scale computer is one where the platform is designed from the ground up for power and energy efficiency, okay? Our goal will be to just go back to the drawing board and think about how one would design a many-core if power and energy consumption is #1 constraint, and you're willing to do anything to keep this low, okay? Or another definition of an extreme-scale computer is a computer that, or a platform that is 100 to 1,000 times more capable than current machines for the same power consumption and for the same physical footprint. Okay, so give me a machine today with a certain performance, a certain power consumption, and a certain physical footprint, and build another one that has the same power consumption and the physical footprint, but it's 1,000 times more powerful. Okay, so terascale telephone, right? Telephone that is a terascale, or an exascale machine that consumes the same as the biggest supercomputer today. Okay, so that's why we're looking at all these technologies that I talked about before to be able to think about how to build these types of architectures. Okay, so what are the characteristics of extreme-scale computing? It applies to all the layers of the computing stack, starting from circuits to architecture to runtime systems. Okay? Necessarily relies on a high degree of parallelism because we're going to deny high frequencies. We're not going to use high frequencies, okay, because we're going to try to be looking at low voltage. And this high degree of parallelism is okay, because if we don't use something, we're going to shut it off. Okay, we're not going to keep 1,000 processors on all the time. We're going to shut as much as we can. It will be technology that is applicable to all the platforms, from high-end systems, exascale, departmental petascale machines, to telephones, handhelds, tablets. Okay? And it's intimately associated with resiliency problems and programmability issues. Okay? If I have a 1,000 core chip, how do you program this thing? Okay. If I reduce the voltage so much that I start seeing aging errors, how do I handle resiliency? So just to give you an overview of what we're looking at, so the building blocks of this extreme scale architecture environment is all over the stack, right? So you start with, first, you want to look at new technologies that are more energy efficient than current ones. So 3D die stacking is very important, right? Photonics, all these technologies that are promising a quantum step on energy efficiency. At the circuits level, you want low power resilient circuits, and that means NTV, and as I said before, it means also super aggressive leakage power management. Okay. At the architecture level, you want a very streamlined architecture, okay, organize the chip in clusters, okay, to benefit from locality and from process variation. You also want very simple cores, say 1,000 simple cores with possibly accelerators. You want to support fine-grained synchronization in the architecture because you will need a lot of parallelism, right? And you also want to minimize data movement in the architecture because power is spent moving data around. So you want group moves in the ISA. You want computation close to the memory system. Okay? At the runtime system, you want to be able to manage the memory hierarchy. You may not want to leave the cache coherence protocol to actually do the movements for you because it moves some useless data. Instead, you want to use scratch pads and ideas from embedded systems. You want to support fine-grained tasking because there'll be 1,000, 10 times maybe, or 2 times the number of processors in terms of tasks. At the compilation tools, you want to have compilers that understand locality and manage locality as much as possible, minimizing data movement. It's okay to replicate computation if that saves you movement of data. And at the programming model, you want to allow the programmer to express a hierarchy of locality. It's very important to be able to express locality when you present or when you define the algorithm, right? And especially for low-skilled programmers, they want to be able to think about a hierarchy of localities. And then for more expert programmers, then you may want to give full machine control. Hooks in the machine that allow them to place data where they want, to move data, fancy instructions, and so forth. And then on top of that, then resiliency, as I said, is a challenge, and programmability are all challenges. So that's my last slide. I should finish thanking a bunch of students who have contributed to this work, okay, and a professor in Wisconsin as well. And that's it. Thank you.